So we're going to collect an OSL sample right now, optically stimulated luminescence sample. That's a fancy term for saying we're going to date the last time that these little sand grains were exposed to sunlight. These ones right now are exposed to sunlight, so they're no good. So we have to go into the original sediments that were deposited in this beach environment and extract some grains from there without exposing them to sunlight. We have a regular piece of PVC pipe that's been sharpened on one end, and we have this metal cap on the other. I'm going to take a sledgehammer and pound this in to that wall of that little pit and then extract it without exposing the sediment to light that's in this tube. And then this tube will go back to the lab, and that's when the magic happens. And so now I have this PVC pipe full of sand, and this is what we're going to package up and send to the lab.
So we're using a dosimeter. We leave it in here for half an hour in the hole that we retrieve the sample from in order to collect the environmental radiation that we use to calculate the dose rate and determine the age of the sand. As it's working.
And so we've been out here for a while looking for shells so that we could radiocarbon date these shells and figure out how old these beach features are. We were looking last year, we were looking earlier this week, no luck. But then I remembered that my friend Mara Threeheist from the USGS was out here a couple of years ago and told me she found some shells in some of these beach ridges. So I called her up a couple of days ago, and she directed me to this outcrop right here. And lo and behold, there are some shells in here. They're not in these gravels up on top of this stack. These are beach gravels, but they're in these fine-grained deposits beneath these gravels, and they're right here, an inch or two, a few centimeters below this contact between the fine-grained deposits and these beach gravels. And I think that these two deposits are part of the same kind of package. These are lagoonal deposits that were ponded behind this beach ridge when it was active, when there was a lake on the other side of it. And so there was some little calm water back here, and these snails were living in here. And there's several kinds of species of snails. I haven't identified them yet, but I picked one, a single species to collect, and we are going to submit that to a radiocarbon lab.
We're on the southwest margin of Coal Valley, above where it starts to transition into playa, and below most of the alluvium and the highest beach ridges of pluvial Lake Coal. The reason that this profile is important is because of this tephra. This white volcanic ash was deposited when Mount Mazama in Oregon blew up its top 7,600 years ago, creating Crater Lake. That tephra made its way down into southern Nevada and fell from the air to create this deposit. So we have this blanket, this temporal marker from 7,600 years ago. The tephra fell on a horizontal surface of brown silts. So these silts are characteristic of probably playa deposits, possibly weathered or shallow lake. So we know that pluvial Lake Coal had receded before 7,600 years ago.
One of the most stable organic materials for radiocarbon dating is charcoal. So during our fieldwork in Coal Valley, we scoured each cut bank and profile to find charcoal in meaningful context, including this arroyo and water gap. Here we found lenses rich in charcoal associated with darker, more organic rich sediments in the bottom 1/3 of the cut bank. We collected several samples and will submit them for radiocarbon dating to see when these sediments were deposited.